So we saw one simplistic example of being able to use method of Frobenius. So now we're going to take a look at a little more difficult example. So we're going to find two linearly independent solutions about the regular singular point x naught equals 0 for the differential equation 2xy double prime minus y prime plus 2y equals 0. All right, let's start by dividing everything by x. So we're going to get 2y double prime minus 1 over xy prime plus 2 over xy equals 0. The solution that we're going to give is that, oh, and notice that x sub naught is indeed a singular point because it appears at most one time in each of the denominators of the coefficients. So we're going to have y equals series n equals 0 to infinity c sub n x minus 0, or just x to the n plus r power. Our derivative, y prime, is going to be series n equals 0 to infinity. Again, we don't change the bounds when we take the derivative because of the r. C sub n, n plus r, x to the n plus r minus 1. And then our second derivative, again, not changing the lower bound, 0 to infinity, c sub n, n plus r minus 1, and then x to the n plus r minus 2. And all we get to do at this point is now substitute that back into our original differential equation. All right, so it's going to get a little bit ugly. So now the dE is going to become 2 series n equals 0 to infinity, c sub n, n plus r minus 1, x to the n plus r minus 2, minus 1 over x times the first derivative, which is n equals 0 to infinity, c sub n, n plus r, x to the n plus r minus 1, and then finally plus 2 over x times the original series, n equals 0 to infinity, c sub n, x to the n plus r. And all of that's going to be equal to 0. All right. The whole reason we have these series, let's go ahead and factor the x's back into the series. All right, so we're going to rewrite. And I'm just going to separate each of these with some lines so that way we know what step is next. So now this is going to become same second derivative, so n equals 0 to infinity, c sub n, n plus r minus 1, x to the n plus r minus 2, minus, so we're going to factor the 1 over x, and that's really an x to the minus 1, so this is really just going to become x to the minus 2 power. So now we have series n equals 0 to infinity, c sub n, n plus r, x to the n plus r minus 2, and then finally we're going to factor an x into, or an x to the minus 1 in here, so that's just going to be n plus r minus 1. So that's going to be plus 2 series n equals 0 to infinity, c sub n, x to the n plus r minus 1. And all that's going to be equal to 0. All right, so how is this unlike the other problems that we've seen so far? Well, now we can't factor out the series yet because what we notice is that we have different powers for the x's. They're only off by 1, but they're still off. So this is where we're going to go back to our old friend change of variable. We need to go ahead and increase the first two series in this sum by 1 because we have n plus r minus 2, n plus r minus 2. We want to make it look like n plus r minus 1. So the substitution that we're going to use for each of those is we're just going to let n be equal to k plus 1. We're not worried about r. So n is going to be equal to k plus 1, n is going to be equal to k plus 1, and then for the last series, n is just going to be equal to k because we don't necessarily care about changing the index. Now, or I'm sorry, changing the exponent. Now that means that in the first two series, we are going to change finally the indexes. All right, so remember that n minus 1 is going to be equal to k, and that's going to change the lower bound for these. All right, so let's see how these are going to change out at this point. All right, so for our next line, now we're going to have two series k equals -1 to infinity, c sub k plus 1, which we haven't seen yet with a method of Frobenius to where we change the c value. We're going to substitute k plus 1 in for n, so that's going to be k plus r plus 1. If we substitute k plus 1 in, this -1 right here is going to go away, so we're just going to get k plus r plus 1 minus 1, x to the k plus r minus 1. Now we're going to have minus the series, so we're changing this series, the second series as well. So we're going to have a k equals -1 to infinity, c sub k plus 1, k plus r plus 1, x to the k plus r minus 1. And then finally the last series is just going to replace n's with k's. So now we're going to get two series k equals 0 to infinity, c sub k, x to the k plus r minus 1, and that's all going to be equal to 0. All right, so at this point, we still can't factor out that series as well as the x to the k plus r minus 1. Even though we have all x to the k plus r minus 1s, we have to get the indexes to look the same. So what we're going to have to do is, from those first two series, we're going to have to break off k equals -1. So we're going to sub k equals -1 into our first two series. All right, and this is the old trick that we've done. We always pick on the lower series. All right, we try to bring it up to the other series. All right, so let's be careful when we do this, okay, because it's obviously easy to make a copy error. So we're going to have 2 c sub naught, all right, so just plugging in right here for k equals 0, or k equals -1, excuse me. -1 plus r plus 1 is just going to be r, and then we're going to have k plus r, so k is -1, so that's going to be r minus 1. All right, and then we're going to have x to the -1 plus r minus 1, so that's going to be r minus 2. All right, so that's for the first series. Now for the second series, minus c sub naught, k plus r plus 1, -1 plus 1 is going to be just an r, so it's going to be c naught r. And then we're going to have an x to the r minus 2 again. All right. Now what we can do is we can just shift all of the indexes up to 0. All right, so we're just going to copy the entire series back over. So 2 series k equals 0 to infinity, c sub k plus 1, and then that's going to be k plus r plus 1, k plus r, and then x to the k plus r minus 1, minus series k equals 0 to infinity, c sub k plus 1, and then I think we have a k plus r plus 1, x to the k plus r minus 1, and then finally that last series, so we're going to add 2 of k equals 0 to infinity, and we're going to have c sub k, x to the k plus r minus 1. And that's going to be equal to 0. All right, so at long last, we can finally factor the series, and then we can also simplify these c naught expressions. All right, and remember, c naught cannot equal 0 when we're doing this. All right, so by simplification, those first two terms become 2 times c naught times r squared minus r, okay, or we just say 2r squared minus 2r. It doesn't really matter at this point. And then we have the x to the r minus 2. which does matter. And then minus C naught R x to the R minus 2. And now we're going to factor out the series. All right, so we're going to factor out series k equals 0 to infinity x to the k plus R minus 1. And that's going to leave us with a pretty big mess, but at least we don't have the series any longer. So now we're going to have C sub k plus 1, k plus R plus 1, k plus R, minus C sub k plus 1 times k plus R plus 1, and then finally plus 2 of the C sub k's. And that's going to be equal to 0. All right, so let's see what we can get out of this. All right, so we know right away that x equals 0 is a trivial solution. All right, who cares? We don't really care that much about it, but I'll just mention it. Another thing that we notice is that these terms have to be equal to 0, and that's going to give us our indicial equation, or our indicial roots. All right, so notice that we can factor out an x to the r minus 2, and we can factor out a c naught from that. All right, so let's do that. So if we factor out c naught x to the r minus 2, that's going to leave us with 2r squared minus 2r minus r. Right? Or and equals 0. Or in other words, we can clearly see that if this becomes minus 3r, we can factor out an r, be left with 2r minus 3 equals 0. And fortunately for us, it's really good news, that we get that r1 is going to be equal to 0, and that r2 is going to be 3/2. And why is that good news? Because we have a case 1. Because clearly, these do not differ by an integer. All right, so case 1, they do not differ by an integer. All right, so that's good news. All right, so that's where we get that indicial equation from. All right, it's the indicial roots in that case, as well as the equation. Now, the other thing that we have to concern ourselves with now is going to be the recurrence relation. Or in this case, it's going to be recurrence relations. All right, and that means that we're going to take whatever's left over and set that equal to 0. All right, so for the recurrence relations, we have c sub k plus 1, and then we have k plus r plus 1, k plus r, minus c sub k plus 1, k plus r plus 1, and then plus 2c sub k is equal to 0. All right, and so how does this help us? All right, well, remember that we just found the roots for r. We found that r1 is 0 and r2 is going to be 3/2. So in the next video, what we're going to do is we're going to substitute those back in. We're going to get 2 recurrence relations, and then we're going to go ahead and to be able to figure out what the two linearly independent solutions look like.